the feedback or the user preference that we are using in this quote. Okay, but for a recommender system to work, we need to build the user profile, or we need to model how, the preferences. And well, what do we do when we don't have this feedback from the beginning? Okay, we have to gather user feedback, and we have to build this user profile. For doing that, we can run active learning algorithms that they try to infer, or they try to select in a smart way what kind of what specific items we should ask the user to rate. Okay, so instead if we want to build the user profile, instead of just asking random items, we can run some strategies in order to build this profile the most let's say wisely way. Okay, so for example, if this is our domain, here we have the items, and we already know, for example, these two items preference of this user, and an active learning algorithm asks which of two new items should ask the user to rate, right? So, and the active learning algorithm will choose between one of these in order to maximize the information acquired with the fewer ratings items asked. So, for example, in this case, maybe we can select that one because it explores a different part of the space instead of the other one, which is closer to the other point. Okay, that's a strategy, but there can be others. Okay, so our work, what here we are presenting, it's an active learning algorithm that is based on aspect opinions that are extracted from textual user reviews. And again, I would like to point out that the objective of an active learning algorithm is not to improve the recommender systems, but to get similar recommendation results or metrics, but with fewer items asked. Okay. This is the plan for this session. We have already seen the motivation, and we are going to do an overview of the active state-of-the-art active learning methods, and then we are going to see the experiments and the conclusions. Okay, we can split active learning algorithms between personalized or non-personalized. The point here is if we take into account users' previously expressed ratings. In that case, if we don't consider previous ratings, we will be suggesting all the users the same list of items, and if we do, it will be personalized because each user will receive a different list of items to rate, and we can have single versus combined heuristics. The key here is if we use only one selection rule, or if we combine several selection rules in order to improve the algorithm. Some examples, for example, a very simple one is popularity. Just suggest the items which are more popular. This is key because if we ask a user to rate an item, the first thing we need to do is the user to know the item. So that's why popularity is something important in active learning. We can also have variance or entropy, with somehow they assume that it's important for the system to know what a user thinks of a rating of an item which is some controversial. If an item has different positive and negative things, it's controversial, and it's very good for the system to know what a user thinks of it. That's why we use variance or popularity. Regarding the personalized, we can have item-item model algorithm, which suggests the user items which are similar to other previously rated items. That's the reason for that, is that, okay, we are assuming that the user will know the item because it's similar to others. Okay, so that is active learning methods in state of the art, very brief summary. And the proposal method here is a one based on aspect. The idea here is to exploit the rich information that can be extracted from reviews, the aspects and the opinion about them. And we want to help the user to find items that share characteristics with previously interacted items. And we are assuming that the aspect information, in contrast to other content or collaborative information, should alleviate better the cold start problem. In particular, we are using for this active learning method, we are using a hybrid recommendation approach presented in Rexis last year. It's built on aspect-based item similarity matrix plus the collaborative information. In this case, the similarity matrix is computed by using the cosine similarity between two items, and the item profile is built on top on the aspect. So just take your favorite aspect extraction methods, build the item profile, and compute the similarity between them. And you can you then build the hybrid approach, and you just suggest the users with these items, right? So this is included in the item category that we've seen before. Yeah, so therefore it's personalized and single heuristic. Okay, let's go for the experiments that we've run in order to test this algorithm. We are using the movies and TV Amazon product reviews datasets, and for the ratings, the items and the users, and for the aspects, we are using the vocabulary methods, the aspects extracted the vocabulary method presented in this work. These are the big numbers. After filtering, we have around 800,000 of ratings with 14,000 users, around 48,000 items, and almost 400,000 annotations. And we are using 23 aspects. Okay, for the experiments, there is a footnote there that we have to do more sampling in order for computational reasons for this. The methodology, in order to run experiments, and we take the whole data set and we split 30% for test and 70% for, let's say, training. But we start just with a small portion of data, 2% of it will be our training set. And at each iteration, we run an active learning algorithm over the candidate set. Our algorithm suggests a list of items. We ask the user to rate them. And if the user knows the items, and their ratings will be included in the training set. Once we have that, we feed our recommender system model. In this case, we are using SVD, and we compute the metrics, the recommender system metrics over the test set. Okay, we run this a few times. In our case, we are doing 170 iterations, and we compute these metrics on each iteration. We are also suggesting in this configuration 10 items per user per iteration, and we are running also cross-validation with 3 false for the data splitting. Okay, the metrics, it's important to recall here that we are computing both rating metrics such as mean average error, mean absolute error, or RMEC, also ranking metrics such as precision at K. Okay, and for the baseline, we are comparing this proposed algorithm with 5 with 5 baselines. These are very good baseline despite of their simplicity. And now let's go to the results. Okay, the first one is we want something that is done in active learning is computing how many items the user know, how many of the suggested items the user know. Why? Because if the user doesn't know the items that she is being suggested, she won't be able to rate them. So here we compute numbers of ratings in each training step, in each iteration that we are included into our training data set. Okay, here our method is the yellow one. You can see that it's not one of the best. Okay, it's not very good at finding items that the user knows. That's something not, let's say, not very good results, but we will see how it affects the ranking and the rating metrics. So here we are showing how the mean absolute error decays. So remember that the objective is not that our mean absolute error to be low in general, like in our system, but we want that the active learning algorithms gets the highest improvement in error. Okay, and here we can see that the yellow line is our method gets the biggest, the highest decay. So it's getting a very good result in comparison to the other algorithms. And what about ranking metrics? Okay, here we are presenting precision at 5, and we can see that in the first iterations, the yellow line is above the others. Not every iteration, but it's on the top part. But also from iteration number 8 and so on, it's always better than the other methods regarding the items that it's selecting leads to better ranking precision ranking metrics in the recommender system. Okay. So just to sum up, we in this work have presented an active learning algorithm based on opinions about item aspects. To the best of our knowledge, it's one of the first works that use aspects for active learning. We have tested it in a real world data set. We have tested in a real world data set, and we have seen that it outperforms other active learning
Vado in
strategies.
camera perché devo sentire la conferenza. Ok.
Sorry, Monica, I cannot
Monica,
I cannot mute your microphone. I don't know why. Monica, your microphone is not muted.
Perché c'è questa scatolina da hacker, no?
non so.
Monica,
Tu l'hai voluta
Fabio?
lasciare per la lampadina, per sapere quale lampadina
Monica?
prendere.
Monica, Fabio?
L'hai presa già?
Monica, Fabio, your microphone is unmuted. I cannot mute. So sorry about that. I'm going to try to.
Okay, maybe now it's better. No, I will wait.
Yeah, you can go ahead.
Yeah. Okay, I'll try. So yes, the last point is that okay, this new active learning approach tested on a real world data set we have seen that on this data set it has outperforming other active learning strategies both on rating prediction and also on ranking precision metrics. For the future work, we just would like to run more exhaustive experiments, for example, using more sophisticated aspect extraction methods, but also testing other recommender systems, any effect there, and also in different data sets of different domains. We would like also to analyze how this method works with different cold start settings, because we think this is an important point to analyze. And also, lastly, we would like to run online evaluation with real users to compare these offline results. In particular, we would like to integrate it into a conversational agent or chatbot, because we think this is a real scenario where you start using a conversational agent. You need to build a user profile, and this is a really natural way of doing that. Okay, so thank you for your time, and now we have time for a few questions.
Thank you very much, Maria. So we have a couple of minutes for questions. If you want to speak, please raise your hand, or you can also write your question in the chat.
Okay, hi, Paul.
Hi, Fidel.
I think I raised my hand. Just a quick question to Maria. Very nice presentation, by the way. I enjoyed it very much. Just a very probably stupid question, but can you come back to figure number 3, please?
Yeah.
So these are very nice results, and it caught my eye that your proposal is kind of rising when you, as you said before, starting on iteration number 8, it goes up, and the others go down. Do you have any idea why this may be happening?
Well, to more deeply on that, the main idea for that is, I think it's related to this, that okay, this we are not getting so many items, so probably these other methods are getting more items. They are less less useful, let's say. So I
So
have no
basically-
idea. That's an intuition, but I think that
Okay.
maybe this is getting better items, and from this point on, these are getting just a lot of items, but they are not really useful for the recommendation. But that's an
Yeah.
intuition.
Okay, I see your idea. So you are saying basically that the others are getting more noise and yours is cleaner. Okay, it makes sense. So thank you very much for your
Yeah.
answer.
Okay, good.
Thanks.
More questions? You may, if you want to ask a question, you may just open your mic and speak, because I didn't see the hand raised by here. So I have a short question, Maria, or comment. I think so. You show like two kind of results. One is or two goals, so to speak. One is the ability to discover ratings, right? And you said that your approach does not as good as others. And then the accuracy that you enable for a recommendation algorithm with the discovered ratings. So I guess the important goal is the second one, right? So it doesn't matter much that in your experiment your approach discovers less ratings. First, because in a real setting you would be getting those ratings. It's just that they are not in the data set. So I think that's not something that is
Okay, yeah.
a limitation. And also the second is that actually you are getting less ratings but more informative. I guess you're getting ratings for less popular items, perhaps something like that, and those are end up being more informative. So yeah, I think that's a good,
Totally, yes.
good result.
The main is the second one, but from the user perspective, it's also important to keep the first one, let's say, good enough. Because if you are asking the user to rate a lot of items and she doesn't know them, that's a very bad experience from the user experience. So that's for sure. Totally agree that the goal is the second one, but also the first one has to be somehow controlled.
Yeah, I see. I mean, it's still, I think maybe you can give the user 3 choices, like I like it, I don't like it, I don't know. So
yeah,
but yeah, I see your point.
Yeah.
Okay, thanks a lot. So I think we okay, thanks, Maria. I think we should move on to the next presentation, and it's going to be given by Fidel Cacheda from the University of Coruña. And I think Fidel is going to give us some hope, right, for the new user problem on recommender system.
Yeah, I hope so also. Okay, so thank you very much, Pablo. First, let me thank the organizers, because I just can't imagine how difficult it could be to organize online or this whole conference. So I hope you are seeing my screen properly. As Pablo said, I'm going to present this work, HOPE, High Order Profile Expansion for the New User Problem on Recommender Systems. I'm Fidel Cacheda. I'm co-author with Diego, Braisho, and Victor of this work. I come from the University of A Coruña, from the CITIC Research Center. So this is an outline of the presentation. First, I will start with a brief intro, then I will present some details about profile expansion. That is what we base our work with. And then we will talk about high-order profile expansion and then the experiments and, of course, finally the conclusions. This is an extended abstract from a paper that we published last year on PLOS ONE. Here you have the reference. I don't know if I can try. I will paste the link later. But anyway, it's fairly easy to find. Okay. Okay. So very quickly, a brief intro to recommender systems for some people in the audience that may be not so familiar. We have users, there will be on the rows, and then we have items. In this case, it's movies, but whatever it is. And well, as Maria was saying before, the users will provide ratings to the items in some different ways. We don't care basically about that. Okay, so we get some ratings for the items, and this would be our rating matrix. Okay, and we have the goal start problem, and we specifically work with the new user problem. That is the problem that when a new user comes to the system, we basically don't have much or none information at all, and we have to provide suggestions, recommendations to this user. In our case, we will focus on the problem where we have very few recommendations, very few ratings for the new user, maybe 1, 2, and then we have to provide, we are supposed to provide good recommendations. Okay, so to kind of solve this problem, we presented the profile expansion idea. This is a paper from 2013 on information processing and management. And there we propose some techniques to deal with the new user problem. And basically, the idea is to expand the user profile with more ratings, okay, without the user intervention. This is the basic idea. And this is inspired on query expansion from information retrieval. So this is done, and what we propose here with this HOPE, high-order profile expansion, is to combine 2 or more of these profile expansion techniques, okay? And in a minute, we will see how we can combine these techniques. But first, let me talk a little bit more about profile expansion. Let me move this. Yeah. For collaborative filtering, you know what I didn't say, but we are based on collaborative filtering, and you know that the idea is that we want to find similar users to recommend items. Okay. In our works, we are based on KNN to compute similarity, but anything will do it for us. Okay. And we will find most similar users, then we will get the neighbors from there, and using only these neighbors, we will compute the recommendations. Okay, this is basically the idea of collaborative filtering. Okay. So what we propose in profile expansion? Well, we differentiate 4 different alternatives. We can talk about local profile expansion, where we use information from just the current user. Global profile expansion, if we use information that is independent from the current user. And we also talk about item-based profile expansion, where we select the items to expand the profile among a set of specific, or user-based profile expansion, where the items are selected among those rated by some specific set of users. And this results on these 4 different profile expansion techniques. So we have item global, where the items similar to the item in the user profile will be decided according to some global information, such as general user opinions or content-based features. We have item local, where items recommended by the algorithm using just the original user profile. We have user global, And I have to say that we won't explore this variant here, this alternative. It's basically using global information such as demographic data from the user. So we are not working this side. And finally, user local, where items rated by those by the neighbors chosen by the algorithm according to the user's opinions. Okay. So let's focus a little bit on each one of them. First, we have item global. So these are the items that the user has already rated. So we will find similar items, checking whole items on the data set. Okay. Item local, we will reach to this final point somehow. Okay, so we'll reach this recommendation, and then we will enrich the user profile using these items from the sum of the items from the recommendation. Okay. User global, as I said before, we are not evaluating it. It's basically working with some demographic data for users. And user local, we reach this point. We get the neighborhood, and then from the neighborhood we will select some items. Okay, and here we have different alternatives. One very simple and straightforward will be most rated, and you will see in a minute that it works pretty well. Some more elaborate are local items neighborhood, where most similar items from the local neighborhood are selected. User local clustering, where only ratings from local user neighborhood are taken into account, and you can see on the paper we use a different similarity to get to this point. Very briefly, from profile expansion, we can see that item global works pretty good. I mean, we are able to improve by 80% precision. It's fairly simple, and especially it works very, very good for one rating users. Okay. On the other side, we have user local, that it's a little bit better. We are able to reach 100% precision, to improve, sorry, by 100% precision. And as I said before, most rated works very good. On the other side, item local doesn't work very, very good at all. So what about high order profile expansion? So the idea here is that we will take this profile expansion technique and we will combine them. So we will consider, on this work, we only consider two techniques to see how they work and which alternatives are better. And we will focus on the two better ones, item global and user local. And we will combine them in a serial or a parallel. So on a serial, we're basically doing a pipeline. So here we will first run expansion algorithm 1, and then with the expanded user profile, we run expansion algorithm 2. And finally, we get expanded user profile and the recommendation. Okay, this will be serial. And parallel, we run the two algorithms on parallel, and then we combine them. And for the combination, we tested the union of these items rated and the intersection of these items. Okay. So for our experiments, we work on the movie recommendation domain. We are using the Netflix movie data set, and we limit the movies to those that appear on IMDb. So we are working with roughly 8,000 items, 478,000 users, and 48 million ratings. For the experiments, we take 1,000 users for evaluation purposes. We use giving n strategy, and only n items are part of the training set, and we focus on very small users with very, very little ratings, with especially n equal to 2, although we will see some graphs with different values for n. And we are using, for the similarity, user base KNN, and we will measure our performance with precision at 5 and mean average precision. So this, I will try to be quick here. These are the results for basic profile expansion. So this is just one profile expansion algorithm. This is the profile expansion size. This is an L, although on the slide is not very clear, but it's an L. Here we can see item global, where we can see that the best results are obtained with small values of L, specifically with small perfection size, L equal to 2 or L equal to 5. This will be user local clustering, and this is user local neighbors and user local most rated. And from this, well, I'm sorry, I didn't mention it, but this is the baseline, no profile expansion at all. So the main idea here is that using profile expansion, we get better results than without it. And you can see that for user local, this is the best values. Most rated gets the best results here and here. Okay. So just summarizing for basic profile expansion, item global works pretty good. Okay, we get best results for L equal to 2 and L equal to 5. If the profile size increases, the results worsen. And for user local, results are kind of similar, slightly better for most rated, and we prefer this option because it's simple. Okay. And from now on, we will use as baselines no profile expansion, of course, and the best results, that we achieved with user local most rated. Okay, with this configuration over here. So this is the high order profile expansion, the serial combination. So this would be algorithm number 1, and here you have algorithm number 2, and this is the second table. It's not very easy to see on the slides. It's far easier to check it on the paper. Okay. Just summarizing, you see that if you check the results, that user local neighbors, it's better when it works first, and item global is better as if it works second. And it kind of makes sense because when the user information is really scarce, global information may introduce more noise, more errors than local information. So it makes sense to use first some local algorithm and then some global algorithm. On the next slides, we will study more deeply this area alternative, and we will check different combinations. Okay, so here we can see the item global. Sorry, I have to move this. Okay. The item global, you can see that this is the best result that we achieved for n equal to 2. And this is the combination of most rated and item global. And we are able to improve 10% the best baseline for the profile expansion. And we are combining both types of information. And also we can see that as we increase n, the precision tends to decrease. This also makes sense because as we increase n, there is no scarce information. Okay, so probably what we are doing at this point is to introduce more errors on the results than anything else. Sorry. Okay, this is the user local alternatives. Again, we have here the best result, that it's most rated local clustering. It achieves the best precision at 5. And the good news here is that it keeps still being the best at when n is equal to 10. But the mean average precision is worse. We are not achieving very good results here. And finally, this is we are trying one algorithm with itself. So these first 3 are okay. Sorry, I will try to hurry up. These are the algorithm by themselves, and you can see that when we combine them, we tend to achieve better results. Okay, especially for item global, local clustering, and most rated. Okay, so this implies that it's better to use a serial process than to double the profile expansion size. And very quickly with parallel, this is the intersection where here we have to obviously increase the profile size because otherwise the intersection would be empty. Overall, we achieved good map, but poor precision at 5. And for the union, the results are not very, very good. That's the main point. So to conclude, one very clear conclusion is that serial performs better than parallel. We are able to improve by 10% basic profile expansion techniques, and of course 110% no profile expansion. And the bottom line here is that most rated combined with any other, it will always improve the baseline. And as future works, we would like to explore the combination of more than 2 profile expansion techniques. Especially, we would like to see where it doesn't make sense to continue adding more techniques. We like to try more the parallel alternative with other merging techniques and stuff like that, and of course other collaborative filtering algorithms. Okay, sorry, I'm over time, but I hope everything is clear.
No problem, Fidel. Thanks a lot. So we have time for some questions. I think we have a question from the audience. Let me say, I don't know, for some reason I cannot see the raised hands. I tested
Pablo.
it with Ivan, and so yeah, Max. Yeah.
For your presentation. Just a little question. Did you try to change the combination between the 2 algorithms while n is increasing? To say, did you try to change such combination while n is increasing?
We didn't, and actually it's a good idea. Yeah, I would love to try that. Yeah, probably it makes sense actually to try to change the combination as you're increasing n. Yeah, good point. Yeah, so sorry, we didn't try it, but I hope we can try it in the future. Thank you very much for your comment.
No problem.
Ivan, you have a question?
Yes, I have a question. I raised my hand, but it seems you cannot see it. Anyway, thank you. Thank you, Fidel, for the presentation. If I understood correctly, the item global method is based on content-based similarities. So which features did you use? Could you explain a little bit how the similarities are computed?
No, I'm sorry. I didn't explain it clearly, but we are not using content-based, but the whole data set. So we are using ratings anyway.
Only ratings and not content-based features, just ratings.
Yeah.
Okay. Did you try with content-based features or not? Because in the cold start, normal, it's useful to use content-based features because you don't have enough ratings. So.
Yeah, I agree, but we didn't try it. That's the truth.
Okay, thank you.
Thanks.
Okay, thank you, Fidel.
Thank you, Pablo.
So let's move on to the next presentation. This is the next presentation is a paper about similarity between trajectories in location-based social networks, and it's going to be presented by Alejandro Bellojín from Autónoma University of Madrid. The title is Analysis of Co-Movement Pattern Mining Methods for Recommendation. Alex, you can start anytime.
Okay. Thank you, Pablo. Can you see my presentation?
Yep.
Oh, okay, great. So, wait, this, okay. Yeah, so hello, everyone. My name is Alejandro Bellojín, as Pablo introduced me, and I'm here to present this extended abstract that presents a project I started with one of my bachelor students, Sergio Torrijos, about how to apply trajectory pattern mining, and in particular, co-movement pattern mining methods for recommendation. So I'm not going to talk about recommender systems. You already know about them from the previous talks, but just the basics. So we have users. In our case, we don't have ratings. So I'm going to present it in the general way that the users interact with items. And the goal is to predict which items a user will like based on the previous experiences, the content of the items, and so on. In this project, we focus on the tourism domain, which has some particularities. So first, the items are venues or points of interest, POIs. They are located in a specific place, so they have geographical coordinates. And the type of venues is very important. In fact, we can classify the types of venues according to their categories. These categories can be restaurants, museums, parks, and so on. The geographical coordinates can be used to make reasonable recommendations. For instance, we can recommend C, then E, and then K, but this may not be very useful for the user. However, it might be better to first recommend K after C, and then E. In fact, the order in which users visit the venues is very important, and it is something we can exploit as sequences of interactions. Moreover, these sequences can be interpreted as trajectories if we understand the users as particles or any other object. Because of this, and in this project, we propose to explore the use of trajectory pattern mining methods for recommendation. This is a very broad area, as you can see in this summary presented in this survey. Some tasks addressed by trajectory pattern mining methods include trajectory processing to remove noise or to detect important points. Also, how to segment or partition the trajectories in different parts and so on. Also, trajectory indexing and retrieval, which some of you may be familiar with, considering the topic of this conference. Also, methods to detect anomalies and uncertainties that can be considered by other algorithms, and other methods that mine the patterns found in the trajectories, like clustering or frequent sequences. So what we actually want to study in this project is how to exploit trajectory patterns for recommendation. We want to move beyond the typical or ad hoc techniques used in recommendation to process touristic information. And for this, we propose to explore the methods presented before that belong to the trajectory pattern mining area. Then the first thing we need is trajectories. Unless we have explicit trajectories, which are very rare in public datasets, we need to process check-in information. So the most common data in the area of tourism recommendation, it comes from location-based social networks like Foursquare, or maybe Google Maps can also be considered as a location-based social network, where the users visit a place and they say where they are. So they check in a place. That's why we say that's check-in data. The problem is that we cannot use methods from trajectory pattern mining in order to process this information, because these trajectories are not so dense. We have very few points. So the idea is that we need to process this check-in data into sequences. For instance, we may need to split the entire stream of check-ins from one user into different sequences or trajectories. For this, we got inspiration from methods from information retrieval and how the sessions in search or e-commerce are identified and split, mostly by using temporal heuristics, which we extended in this work with spatial heuristics, and were presented in this recent paper was published in UI. Okay, so once we have trajectories, we propose two tasks where trajectory pattern mining might be useful. The first one is for filtering, where we are recommending something to a user but not based on her preferences, just based on very little information, like browsing or visiting just one item, as we do when we are in Amazon or we are checking a newspaper. Here we have an example from Spotify where we can check an artist and the system will show us related artists. The system doesn't know if we like any of these artists, but they are somehow related. In fact, they are similar. They might be similar according to the content or according to collaborative information. That's not important. We propose to do something similar for trajectories. Basically, we can exploit trajectory indexing methods or clustering or any similarity metrics presented in the area and use this information to present the user similar trajectories, either to based on the last trajectory performed by the user, or maybe because the user liked a specific trajectory in the system. The second task where we want to apply trajectory pattern mining is for actual recommendation. And the most simple method we believe these trajectory methods can be applied to is nearest neighbor recommender. Since we only need a similarity metric, we only need to define one similarity metric, either between users or between items. And once we have that, we can produce recommendations. Because of the previous application, we already know some metrics for to compute similarities between items, but there are also some very interesting methods proposed in this trajectory pattern mining area that could be useful to compute similarities between users. These methods are called co-movement pattern mining methods, and they are investigated in order to identify which objects move together. So as you can see in this example, these methods are used to identify, like in a flock of birds, which objects, which particles, in this case birds, which are actually moving together. In fact, flock is the name of one of these techniques. And as you can see here, there are some variations that identify related things, like whether the objects move one after the other, they are in a track, or if there is some particular leaders that everyone follows. But there are many more methods, and we believe they have a lot of potential in terms of recommendation capabilities. So to test this, we have some preliminary results. We used two data sets, one from Foursquare and another from TripBuilder, where we selected two different cities, Tokyo from Foursquare and Rome from TripBuilder. The main difference, as you can observe, is the number of items, where in Rome we have very few items. But in both cases, the data sets are very sparse. So the problem remains quite difficult, even though these data sets are much smaller than typical data sets in other recommendation domains as the ones presented before. Regarding the methods we tested, we used two trajectory similarity metrics, one based on dynamic time warping and another based on Hausdorff distance. We also test one clustering method, the spatiotemporal DB scan, and two methods from the co-movement topic, flock and convoy. So the first thing I want to show you is about the efficiency. So it's quite obvious that even for Rome, which is the smallest data set, even when we take this entire data set, which is not so large, 60K, some methods like the trajectory similarity methods and even flock, they take a lot of time and flock doesn't even finish. So it's quite obvious, and it's already known in the literature, that these methods are very, very expensive. They are very computationally intensive. So because of this, we developed an optimized version, which we call partials, for the co-movement methods based on subsets. So basically, we subsample the the data set and we apply the original algorithm, but on a subset of the data. And how we select this subset, we use the trajectory similarity metrics. So now, if we check the performance in the same data set, we observe different levels of performance, or not all the methods perform as good as the rest. In particular, these are precision values, and flock seems to get the best results, and also clustering, but clustering depends on the parameters. But what is really interesting here is that the approximated versions, like flock partials and convoy partials, get very similar results to the original ones with, as we saw before, in less time. So we think this is a very positive result. We also developed a tool to visualize this information. Here we can see the trajectories followed by the neighbors obtained by these methods. And what I want to show you is that these neighbors are clearly different. So the neighbors obtained by these two methods, which here we have a similarity between trajectories, the dynamic time warping method, and here is convoy, which is one of the co-movement pattern methods. They produce very different neighbors, which have actually different, they show different trajectories in the map. So we also have other results. These results will be presented next week at UMAP. And in this case, we analyze the behavior from a different perspective. And the main point is that if we are able to somehow label or identify the users, so which users are tourists, in this case, we consider that those that have explored the city in a short span of time can be considered as tourists, then these methods, the methods based on co-movement, are better in terms of novelty with EPC, measured here with EPC, are also better in terms of diversity, aggregate diversity, and also in terms of selecting the next category. So the venue, the category of the next venue to visit. They are not better in terms of actual venue recommendation, measured here with NDCG, because just computing neighbors based on cosine is better, but they are better in terms of these other dimensions. Apart from that, we also found that these methods have a higher overlap with the explicit social network of the user. So we consider this might be a potential line of future work where co-movement methods can be exploited as predictors of social links. So just to conclude, we believe trajectory pattern mining methods can be useful for recommendation, even though there are some computational problems that should be solved. And also, but we think that there are some properties of the recommendation problem that can alleviate some of these problems. Like the first thing is that the data points are limited to actual venues. So we don't have fine-grained GPS coordinates as in the trajectory pattern mining area. And also we can exploit the popularity bias, the well-known popularity bias, to our advantage in order to guide these predictions. It is quite obvious that temporal and spatial information are very important in this domain. Even though using this information is not novel, there are not so many works exploiting trajectories in a principal way, and that's what we want to try with this new project. In fact, we want to also explore related tasks like trip recommendation or successive recommendation instead of just recommending a list of POIs where we recommend an entire route or an entire trip in order to exploit the sequence, which is where these methods are particularly good for. And that's all. Thank you for listening, and I'm ready for questions.
Thank you very much, Alex. So we have a few minutes for questions. Ivan.
Yes. Thank you, Alex, for the presentation. With respect to the last part of your presentation, the UMAP paper about where you distinguish between tourists and non-tourist people, did you consider also the time dimension? Maybe there are tourists in some periods of the year which have some different behavior than others.
Yeah, well, we started filtering out. So as you can see here, we only evaluated on Tokyo. So we assume that we can identify users who are tourists in Tokyo and they may be locals in other cities. So that's kind of natural. And also something I didn't explain because I didn't have time, we perform a temporal split. So we consider 6 months of training and then the next month for test. And we consider that the user is a tourist in these 6 months of data. So maybe, as you say, if we go to another moment of the year, maybe a different subset of users could be considered as tourists. But this is something that is not, so this, how to evaluate this is something people have not paid too much attention so far in the tourism domain. So it's, I guess it's an open question. We did it this way. We think it's more or less fair, but it's true that maybe we can, I don't know, like check other moments of the year or checking even other definitions of what really makes a user a tourist.
Okay, and maybe some events, special events in the year that that somehow adapt, no, or modify, have some impact on the pattern. Right? Okay.
Yes, that's true. Even locals act as tourists at some point, right?
Okay.
So yeah, that's a good point. Thank you.
Thank you.
Okay, so Elot has a question. Elot, I don't think we hear you now. You can, if your mic doesn't work, you can also write your question in the chat.
Okay.
Oh, that's good.
You hear me? Okay.
Yes.
So did you take into consideration the time within the day? Because usually tourists go daytime and locals go in the night or in the evening or during the midday. I don't know your data sets, but this is maybe an information that could help you distinguish between tourists and locals.
Yeah, that's a very, very good point. We didn't consider that, but it's true that we have that information. We have the timestamps, so we can decide to split users according to a different decision. That's for sure. I think it might be a good possibility to explore in the future. Yes, thank you.
Marco, thank you.
All right. Thank you, Alex. Thanks for your presentation and your answers. So let's move on to the last presentation of this session. It's going to be delivered by Mathieu Jedor from Cityscout and Borelli Center. And it's going to be about categorized bandits. So Mathieu, you can start anytime.
So, good morning, everyone. So my name is Mathieu Jedor. I'm from the Center Borelli at ENS Paris-Saclay, and also from Cityscout. So I present my work, Categorized Bandit, that is co-authored with Jonathan Wedek and Vianney Perchet. And it has been published at NeurIPS last year. So I begin this little crash course on multi-armed bandits. So we have K unknown distributions with given expected rewards. We have a time horizon capital T. And at each round, the learner must choose an action, and it will sample from this chosen distribution, so chosen arm. And the goal is to minimize the expected regret. Let's say this is equivalent to maximize the cumulative reward. So the regret is just the difference between the reward of a new record, so capital T mu star. So that is the best, the expectation of the best arm, minus the regret. So two popular body algorithms. So I present two popular body algorithms. So the first one is based on the principle of optimism in the face of uncertainty. So this is known as UCB. As its name indicates, it constructs an upper confidence band on each means for each arm, and it samples the best, and the learner chooses the best arm accordingly. The second algorithm is the Thompson sampling. It's based on the Bayesian principle. So at each time step, we sample from the posterior distribution of each arm, and we take simply the best one. So an interesting fact is what is the lowest regret obtained. So this is a theorem from Ley and Robbins, which say that the cumulative regret must satisfy this condition. So what is important to remember that is that this regret is linear on the number of arms k. So this enters my framework, the categorized bandit. Motivation comes from e-commerce. So as we say, previous bandit algorithm have a linear regret in the total number of arms, which in e-commerce can be huge. But thankfully, there are inherent structure behind the catalog of products, as the products are generally grouped by category. Plus, the customer are generally interested in specific categories. So it doesn't have to present all categories in all products to satisfy their needs. So as I said, the objective will be to reduce the linear dependency on the total number of arms. And our work can be viewed as a specific instance of structured bandits. So more formally, we have we have M categories and K arms per categories. So the K is without left of generality. It's just to simplify the notation. And furthermore, we make the hypothesis that one category is better than the other, and that this relation of dominance is not to the learner. So I will mention the dominance we will consider in the next slide. And the goal is also to be to minimize the regret, the cumulative regret. So we will consider three assumptions of dominance in this work. These are gradually weaker, so that the setting is more and more general. So the first one, is the group sparse dominance. So here we assume that we know a threshold. So if we consider just two categories, this means that the expected rewards for one category of one category are all better than this threshold, and for the other categories, they are all below this threshold. The strong dominance is a little weaker. So we have the same, is similar to the previous one, except that we don't know this threshold. And we consider another weaker dominance, that is first order dominance. So here we put a discrete uniform distribution of the means of one category, and then a category is represented by a simple random variable, and we use first order stochastic dominance for random variables to characterize the first dominance in the case of categories. So a simple illustration of this dominance. So here we have three categories with 3 arms per category. So it is immediately we can see that category 1 strongly dominates category 3, And if this value, the common value is known, we will have a group sparse dominance. For the, we also can see that the category 1 first order dominates category 2, because when the two categories have the same number of arms, this simply means that if the means of inside each category are order, this simply means that the KM best arm of category 1 is better than the KM best one in the other category, which is verified here. And we can also say that category 2 strongly, first order dominates category 3. Okay, now we have made our assumption, but are they verified in practice? So here we provide empirical evidence for that. So we collected the click-through rate in 4 different categories over a period of 1 month on the e-commerce website Cdiscount. And we select the 10 best one in each category. So category 1 to 3 are 3 of the largest category in terms of revenue, while category 4 is a smaller one. Here are the results. So here we represent the cumulative distribution function of the 4 categories. So here we can see that the category 1 strongly dominates category 4. The worst arm in category 1 is better than the best arm in category 4. And the same applies for category 2 and category 4. We can also see that the category 2 first order dominates category 3, as the cumulative distribution function of category 3 is always greater than the one of category 2. And interestingly, we have 2 incomparable categories, sorry. That is category 1 and category 2. But actually, the best arm of category 2 is so much higher than the other that we can expect that it is an outlier. And assuming the assumption of dominance will still give great results. So now we talk about the lower bounds. If we assume our assumption of dominance, that in the unstructured case, the regret is linear in the total number of arms. That is, in our settings, it is m times k. And if we assume the group sparse dominance, we can prove that the regret is linear in the number in k. So it's a number of arms in the one category. And furthermore, all these k arms belong to the optimal category. In the strong dominance, so that's a weaker notion of dominance. So just we don't know the threshold between the two categories. And in this case, the regret is linear in k plus the m, that is the number of category. So we can see here that what is important is the suboptimal categories are just the worst arm in each category. And finally, in the first order dominance, so it's a little more difficult to understand this formula. But if we remove the term in the parentheses, we obtain the unstructured, the lower bound on the unstructured setting. So we see that this lower bound, the last term is strictly positive, so this lower bound is strictly lower than in the unstructured case. So that's better. So now we present 2 algorithms for the categorized bandy setting. So the first one is based on the idea of successively eliminate suboptimal categories. So what we will do in this algorithm, so at each time step t, we will compute a set of active categories. Sorry. So this set of active categories will depend on the assumption of dominance. and it will be based on the principle of optimism in the face of uncertainty. So in this sense, we will have all categories that have not been deemed suboptimals. And according to the number of categories inside this set, our algorithm will have three strategies. So the first one, if we have no active categories, so that means the optimal categories is deemed suboptimal. So this is not normal. So we will pull all arms inside each category. If they have a unique category in this set, so that means we have found our optimal categories, and we will perform the UCB algorithm inside this category. And in the case we have several active categories, we will have to pull all arms in all active categories. So we provide the upper bounds on the cumulative regret of this algorithm for all notion of the assumption of dominance, and we can they all are in the full paper. So the second algorithm is based on the Bayesian principle. So it is similar to Thompson sampling, except in this algorithm, which we call a Murphy sampling, we do the sampling with respect to the assumption of dominance. So in practice, we do that by realization sampling. So we sample from each arm until our assumption of dominance is satisfied. And for this algorithm, we do not prove any upper bounds. So it is a future work. Now we present two experiments. So they all are in simulated data. In the first scenario, we regroup the experiment in the sparse and strong dominant case. This is just, I recall, this is just the lack of knowledge of the threshold for the last dominance. So we have 5 categories, 5 arms per category. All arms are Gaussian distribution with unit variance, and the following means. So in all categories, we have a good arm, a bad arm, and some arm in the middle. And we represent the cumulative regret of the various algorithms as a function of time. So we compare our algorithms to the two unstructured bandits I have presented at the beginning, so UCB and Thompson sampling, and with the UCG algorithm, which stands for dense on tree. So this UCG algorithm considers the category structure, but not that one category is better than the other. So we represent the result in this figure. So we can see a lot of things in this figure. That so we see that the UCB algorithm is the regret of the UCB algorithm grow faster than any other algorithm, and it is outperformed by all these algorithms. And if we compare the CAT-SE algorithm, for in the case they assume the sparse dominance, it's a group sparse dominance. Donc it is in red, and the one we assume a strong dominance, it is in purple. So we see the huge difference with the threshold, the knowledge of the threshold makes. And for the Murphy sampling algorithm, they have both similar performance in the two cases. And for the UCG algorithm, in this scenario, the UCG algorithm perform greatly, but it will not be the case in the next one. So in this second scenario, we'll assume the first order dominance. So we have 5 categories with 10 arms per categories. The arms are also a Gaussian distribution with unit variance. and the following means. So actually, so what we can say about this means is that so the best time is in the optimal category, you see, but the other, this second, third, and fourth best time are all in the suboptimal categories. So this is a typical case where we want to exploit the knowledge of the structure to improve the regret. So we compare the previously mentioned algorithm in this case. So we can see that the unstructured algorithm, Bundy algorithm, so the UCB and Thompson sampling are outperformed in this setting. And the UCT algorithm completely failed to converge to a good solution, while our algorithm have a great performance. And we can also say that for the CAT-SC algorithm, for the cost of the exploration phase, so where we sample off arm is huge, and we can see that in this regret. So the regret of the CAT-SC algorithm is more than the double of the one of Murphy sampling. So to conclude, we have introduced a novel Bundy model inspired by e-commerce. We confirm the veracity of the model on the real data, and we provide an algorithm that leverage the structure of the model with their theoretical guarantees. And furthermore, interesting direction include a better exploration phase in a CAT-SC algorithm, as we see it greatly negatively impact the regret. Another challenge is the analysis of Murphy sampling to prove that it works as expected. And another interesting derivation could be the adaptivity to unknown dominance. As in this work, we assume that the dominance is no, which may be not the case in practice. Thank you.
Thank you very much, Mathieu. So, any questions? If you have a question, you can just open your mic and speak up. Okay.